Welcome back. Today we're going to take a look at Lab 3 or Case Study 3. And what you're looking at here is actually, I'll just read off the project. It's a PAP test device controlled brake tip. Now what does that mean? A major medical device manufacturer has developed a new device for performing PAP tests. Its clinical studies indicate that basically may accidentally puncture. This newly designed instrument might actually puncture the soft internal tissue surrounding the cervix. So if you're not familiar with what a pap smear is, it's basically an examination. Women are very susceptible to the human papillomavirus, so are men too, and it can cause cancer in the future. And there's a variety of different versions of the virus, but there's a few in particular that can cause cancer, cervical cancer in women. And so that's why they do the PAP test. It's pretty much a standard test that they do, and they basically it's an invasive test. And this company, this is actually a real world scenario. Again, did something very similar to this, where basically what we have is we had to create a balloon feature on here that would be able to extract a sample from the cervix of the tissue, and essentially you could test the sample, and what they're looking for are abnormal cells. So like, for example, when you have skin cancer, as many of you might know, had a family member who tested for it, like they basically take a chunk of that skin out and they go in the lab and they look under a microscope, or they could actually apply different tests to it to make sure that it's not cancerous or not. And sometimes abnormal cells are precancerous. So that's what this device was to do. It was to be a non-invasive, a less invasive, I should say, procedure for this. What was happening though, as you can see, this is a wand design, and here you have a button that would inflate the balloon, and there was a little tip at the end that was kind of like a if any of you ever played darts, the plastic darts, it's about the same size as that. Well, what was happening is that as it was being inserted, when doctors would insert during clinical studies, is that they found that it might actually, the tip might actually puncture the soft tissue around the cervix itself, and cause bleeding and just discomfort. So they wanted to have it break. Essentially, they wanted a controlled failure, so it would break before it would puncture the tissue. And the doctors, they were hoping the doctors could feel like a feedback given from the little snap of the plastic. So, and again, this design isn't the real design. It's been changed and such since the original. But your task is just to work on the needle here. And the needle, I have Delrin down as it. Delrin isn't really good plastic for this. If any of you wonder what type of plastic Delrin is, just as an FYI, if you flip over your mouse, those little pads that are that glide over the surface of your table, that enables it to glide over the surface, those are actually Delrin. It's a very slick plastic, and it's a bit bendable. It doesn't really break very easily unless it's in a thicker format. So that's not what we really want to use on this one. We're going to use acrylic. The reason being is that we could do using a linear analysis. It just gives us better results for learning. But in real life, we would probably select a different material, not acrylic, because acrylic cracks pretty easily. It could be brittle, and so we wouldn't necessarily use this. But again, we're using it because it's just a good sample, like for learning. So, okay, so let's begin. Let's get that part. First of all, if you go to the, if you go to vertanu1.com, the homepage here, go to the Bracia Initiative, go to Vertanu 2, Manufacturing 2208, and the files are going to be found in Lab 3. So click on Lab 3, download. Click on the needle, and it should immediately launch. It's not compressed or anything, so it will immediately launch. Let's get rid of this fillet. Actually, right-click on that and suppress that. We don't need that. And the reason being is we're going to actually put the force directly on that surface, as if you were hitting it straight on, because that's where we would see puncture occur. So let's go ahead and First of all, make sure you're set MMGS, and looks like mine already is, so we're in good shape there. We're going to go to Evaluate and Simulation Express Analysis Wizard. Now, you'll see it already has a setup, but just for good practice, go to Start Over. Yes. And actually go back for a second. Make sure under Options it's set to SI. Hit OK. Now hit Next. Now add a fixture. And our fixture will be this area here, because this actually has a screw thread on it, a thread that would actually screw into the base of that wand. Let's hit Apply. Hit Next. And add a force. Select that tip there. And set it to IPS. And let's have 10 pounds. And if you're wondering where I get these numbers from, I'm going off of memory, but in many cases, engineers at the company that we work with or at our own company, we would do little tests. You could actually, there's different types of machinery out there and units that could register like torque or PSI and things like that. So sometimes you could figure it that way, or sometimes you could do some hand calculations and guesstimate. So that's usually what you want to get from the engineer who's working on this. And what we're teaching here is mostly for the general designer, the CAD designer, who would apply these features. Okay, so about 10 pounds of force on there. That might be a bit excessive. If I recall, it might have been between 5 and 7 that we really added. But let's hit Next. Hit Choose Material. And again, we're going to go with acrylic, just simply because it's a great material for linear analysis. It gives us some very easy to read results. But you don't pick a material just for the results, remember that, in terms of this is just for training purposes. Okay, hit Apply and Close. Now we could hit Next and hit Run Simulation. All right, hit Yes, Continue. Factor safety of 1. And here we can see there's no red. Show von Mises stress. Megapascals yield. At the very tip, we're seeing the highest stress. And then if you did show displacement, we're seeing like virtually a little bit of flexion occurring in there at the maximum, but not much, 1/10 of a millimeter. So, okay, but what we want to do, here's the test as is. Now the customer came back and said, okay, now can you design in here something that's going to collapse this, help it break? And now when you're thinking of breaking something, like let me just go to markup so you can see this. All right, so imagine you find a couple twigs on the ground and you want to use them as a prop, like a crutch for yourself, like you're out in the forest and you want to use that. Now if you pick a stick that's perfectly straight or as straight as you can get it, and you're basically putting your hand up here and you're putting force down on it, pretty good chance it's going to be very stable. But you pick a stick that might come out like this, and you're putting that same force on it as you're walking, it's probably going to fracture here, break. That's a weak point. So it's the symmetry that gives this such great strength in this, okay? And so we want to actually get this to break. So we want to put in something that makes it, that somewhat breaks the symmetry. Now, you could still keep symmetry and like an accordion type of design, all right? Because in the event that if you break symmetry too much like this, and symmetry is equal on both sides, okay? But when it's like this, it's not equal on both sides because it's bent. So if you bend it though, be aware that as it's being inserted to take the test, if it brushes up against other side walls of tissue, it could break pretty easily on one side and maybe not on the other. So symmetry could be a very important thing when you're designing in failure. Now, what I've had students do, and I thought of this too back when I'm like, gosh, let me tell you what I did with my manager. Right away, we're like, okay, we just want to weaken it, and let's make a cutout here and revolve it. And we revolve this cutout. And so it made it really thin in between here. And then we applied the force. And I remember it was like early morning, my coffee hadn't sunk in. And I'm like, wow, you know, I even bumped it up to like 30 pounds of force and like nothing's happening. Or not much, at least. It's not fracturing, or it's not hitting yield yet. So I realized, I'm like, wait, you got it all wrong here. Again, you have the stick idea here, the symmetry. We need to make some sort of accordion. And so what I ended up doing is, let me turn off edit markup. And normally when we take the class, I usually show this at the end, like after you've all submitted your designs. But being that we're outside of class, and it's very difficult to go back and forth in a day. Like in class, I'm actually able to witness and walk around and see your designs as you're putting them together. So with this online course, that makes it impossible. So I give you the hints here as to what you might want to do. So what we ended up doing for this design is we made an accordion, like on we had to come out like this on one side to cut out, but only went like halfway through. And on the other side, not quite halfway through, but almost, we did another accordion design like this. And so it had like a spring mechanism. So when it got compressed, it actually, and this was thinner materials here, we actually got fracture to occur. And it was stable on all sides as best as we could get it. And it really worked out well. So anyhow, I think it led to a completely redesign of this unit, but at the time it seemed to be a pretty decent solution. So let's see how we would get that to work. So I'm going to turn off markup, go to model, and let's get those out of there. Okay, so now if I select the front plane, I'm going to go to features, I'm going to go to extrude, and hit my space bar, align myself. Now, what we did here, now you could break it on one side, like I said, and it would be asymmetric, but I'll mention that in your design. So if you want to do that, you could. But also I've had students go with like a helix design, and it's not bad. I can't remember what, I think it was just it makes it too flexible on the sides, so when you're inserting it, and it doesn't actually break, but it could still puncture. That was the concern with the helix. But give it a try if you like. All right, so I'm going to go to feature, extrude cut. And, oh, you know what? I don't want it to go through, so I'm going to draw on a line here. Now, I think I also, if I recall correctly, it went something like this too. So I had two cuts, and I just went to features, extrude cut. And actually the plane was offset a little bit too. Gosh, I'm apologize. It's been a while since I did this. So cut on one side there. Oh, you know what? I think we are okay to do it this way. You know, that's right. Select this face and start a sketch. Let's go normal 2. And now we could reverse that, or we could actually flip that around 360 maybe. Let's see here. But anyhow, I'm going to go to sketch and similar style here. I could probably copy and paste the sketch. I'm just going to have a little fun with it though here. Let's align that to that. All right. And I could be using the other tools here to make this symmetric. Again, I'm just having a little bit of fun. And, okay, now let's go to features, extrude cut. I'm not putting any dimensions. I would expect you guys to put dimensions in just so. Okay, and here I get result 0 thickness. And that's what I was afraid of, that we might have to have a little bit of a variation there. Let's see. Cut it that direction. All right, and this is where I believe we ended up putting an insert in the mold to get it through the center, because we had, also it doesn't stick together too well. So let's select this face and go to sketch. Let's try this now. So it was something like that, and then I had another cutout up here. Those cutouts didn't do what I was hoping. Let's delete that. Here, extrude cut. There we go. Now let's go ahead and run that. Now it's, again, it's not perfect. I'd like to see you guys, oh, this is the problem right there. See that little area there? Ah, yeah, that's my problem. That's not coming around properly. So I have to fix that. Let's edit that sketch. Make sure that those don't go all the way to that point. Bring them in a little bit. Rebuild. All right. So it's something like this. So you can see the design. It's more uniform. It's symmetric. It's just kind of changed around. And let's go ahead and try and run it. We save it. And then we'll go back to rerun study here. And click on Simulation Express. Okay, let's show von Mises. And we can see the red. That's good. We're seeing a lot of red there, so we're seeing fracture, or yield at least. Show von Mises, let's see. Here, and where the red line is right there, anything below the lighter blue, so the darker blues are fine. Anything above it, we're starting to see yield, so we're hitting pass yield. And if you remember tinsel on this material, which was about 71, that's where we're looking, it's probably going to fracture, is, I believe that would be up here. So we're seeing that occur, from what I can tell. Again, this is a linear analysis. Non-linear analysis would give us even better results. So, but there you could get your information. Now remember, what you want to do on this is you have to write the report for it. So after you build or make changes to it, and remember, you could design it however you want. All right, this, I'm just showing you like an example in this case. But let's go over here to Vertania1 again. So remember, you go to Vertania1.com, go to Brescia, Manufacturing 2208, and you got the sample case study. You could download that. The training guide's in there too, where it says manual, so you could actually look at it on page, case study here. And the PDF manual is on page 46. I actually have a drawing that you can see, but again, you have to remove the fluff, as they call it. You don't have to make any changes. The only changes I want to see are here. And you don't, oh, and I even had 4 pounds. It's not 4 pounds of pressure, it's 4 pounds of force. I got to fix that. Okay, so that, we'll bring up the document. Why not? Okay, so here we get rid of this stuff. Never use my images. That's, you could get rid of that. You put in here the PAP device. Okay. And here, get rid of this image. And And we're not doing torque. So in this case, it's going to be, we did 10 pounds. 10 lbf, pounds force. Okay, and get rid of this. We don't need that. Now let's bring our image in. So we go back to the model. And we'll do factor of safety first. And keep it a factor of safety of 1 because, again, that's just... and you might be asking, well, isn't factor of safety only if it's a safety concern? In this case, it is a safety concern to some extent, but not in the same way factor of safety is really used. What I found with factor of safety, though, it really is easy to explain to a person factor of safety. And, you know, and so sometimes when someone sees a binary, like 2 colors, red is bad, blue is good, it tells a better story. So in this case, would we really need factor of safety for ourselves? Not really, but it does help. It's another layer of information, but it's also good just because it's a very good descriptor, in my opinion. Again, others, a PhD will tell you, you know, oh, yeah, you probably wouldn't use it in this respect, but for our class, just so, because I want you to try and get used to using these tools, and we'll use it. Okay, and so going back to the study, remember you have to put the purpose, and here should be your own words as much as you can. You could use some of mine. Again, you could use some of the template, but make sure you change these things. Like, again, acrylic is not 60, it's 45. Okay, and drop in a picture. Alt print screen. Control V, get that in there. Format, crop. And I don't want to show you the whole thing. I'm not going to, like the lab 1, if you want to see how the whole thing's done, lab 1 pretty much steps you through it. But these labs are for your own learning. So I want to make sure, I want to see how you guys are doing. And actually put this behind text. There we go. And then you could put in any sort of notes and things like that that you need. And of course, we're going to have to move a lot of this stuff up. But just wanted to get that through. Like in this case, analysis, go to insert, page break to get that out of the way. And now you can make adjustments to these as needed. Or delete them if you're not going to use them. And I don't want to go through the whole thing again because part of this is learning. And remember, this will be, the analysis A will be, you can give me, you don't really need a factor of safety. I want to see it though. Give me a factor of safety of 1 for the first one. All right, and the next one here will be the von Mises. And then, of course, displacement analysis. Actually, I think I have that there. So, all right. So that concludes this lab 3.